Okay, so today we're starting the second half of this chapter on bars. We're going to be doing what are called flexural waves or transverse waves, but most people call them flexural waves. This has to do with a bar bending like this. And we'll find that these are significantly more complicated, as you'll see, but they're very interesting. And so I guess I did this when I first taught this course in 2003. So for motivation, and it's good to have some motivation here because it's going to take us most of the lecture just to derive the equation that describes these waves. It's just not simple, but it is very interesting. So as motivation here, this is back in '99, Physics Today. This is a nanofiber, a very small fiber. You can read about, it's a composite thing, but it's a very tiny fiber. And it's clamped, what we will eventually call clamped. It's effectively clamped down here. And it's resonantly vibrating. They're driving it with an electric potential, and they found resonance here. So you can see, oh, this is being captured. You know, this is two turning points of the motion being captured, and however they got an image of this, right? So that's what you're seeing there, is the two, it's going like this. What's that right there? What do we call that? A node. That's a node, right? And then you can barely, it is vibrating up there. It's going like this. Is this the fundamental mode? No, the fundamental mode is going to look like this. It's going to look like this, right? So we're going to be able to describe all this. And it's interesting, as you can see, as you will see. So this is actually the second mode here. And what the news here, this is sort of the news blurbs here, is that what they did was they resonantly drove this, found the resonant frequency, and then they added a particle, a tiny particle to the top, and then measured the resonant frequency. It went down because of the mass loading. And with those measurements, they were able to determine the mass of the particle, right? And it's a tiny, I don't know what it was, maybe it's mentioned in here what kind of particle it was, but the mass of the particle was 22 femtograms. 22 femtograms. So what's a femto?
10 to the minus 15.
10 to the minus 15 grams. Really tiny. So that's why they call this a balance, a nanobalance. So this utilizing flexure modes. We'll be able to describe all this. And I can't remember, I mean, you know that we're going to be able to handle the mass loading because we've done it before. It's more complicated here, but I don't know whether or not we'll actually do the mass loading, I don't know. But at least the free motion, the clamped free motion, we're going to look at that. We'll mathematically describe that. Here's another example. This was in 2003. And you guys probably remember this. This is the Space Shuttle Columbia disaster. Right, so a lot of you were pretty young. What happened was, not long after liftoffs, there was some debris from an engine or something that hit, impacted one of the wings right here. And the space shuttle had sensors all over it, so they detected. The result of that was, one of the results was, the motion sensors detected that it rang like a bell. Okay, again, this is essentially clamped, like a bar. We could crudely model this as a clamped free bar, similar to the other thing. So it's going to go like this and probably excite at different modes. Does anybody know what the consequence of this was? You guys know about this? I don't know, because
a little more reentry, right?
Yeah. So what happened was, it turns out this had done serious damage here. It opened a hole, and on entry, due to the friction with the atmosphere, it ignited this. It wing and it disintegrated. It was over. Okay. So we're going to begin now with these flexural vibrations. And one of the first things we have to notice is, if we're considering a bar like this, we're going to be able to derive its flexural behavior. But we've got a circular cross section here, right? Well, not all bars not all bards, not all rods, bars. Bard is a not all bars or rods or wires, for that matter, have a circular cross section, right? So this is common, but it's certainly not the only case. Another one is a rectangular cross section. So we will actually deal explicitly with both of these, but you can imagine other types of cross section, and you'll see how it's in the theory, you can handle that if you need to. First of all, I should say we're going to, of course, consider uniform cross sections. If we have a non-uniform rod, that's like a non-uniform string. We did a problem on that related to that, but not here. Okay, we want to take a uniform medium. It's not changing as you go along here. Yeah.
Is there a lot of literature out there based on like I-beams, based on that construction?
Probably.
Yeah.
Yeah. So that's another popular shape. And so why? That's an I-beam. This is the cross section, right? And you'll see in our theory here how you would handle this mathematically. So, what's the point behind it? Why was an I-beam invented? Anybody?
Weight reduction, maybe?
Well, that's part of it, but that's not the basic idea. What's the basic idea of an I-beam?
Increase the moment of inertia.
The stiffness. So this is going to be difficult. If it's running, it's like this, it's going to be hard to bend this way, right? Because of all this material here. But this way it'll be easy to bend the other way. That's part of the idea of an I-beam. I do want to say something about this though. When B is small compared to A, that's what a slinky is made of. Everyone knows what a slinky is, right? This popular spring. Yeah, it's been around since the 1960s or something. I can't remember. Michael, do you know the history? You should. You're doing your thesis on partly on this. So, yeah, slinky, and you can probably play it back in your head. It has a narrow, a flat rectangular cross section, and that causes it to have different properties. And not all those properties are in the literature. It turns out there's two dramatic properties that we think are related that are not in the literature. Nobody apparently knows about them. So we're doing research. That's part of Michael and Kevin's thesis research. Okay, so here's here's a snapshot of a flexural wave on a bar. Okay, first thing I need to say that's not mentioned there is that this scale is not the same as this scale. We've amplified this, okay? Because we're only going to consider small, just like we did with strings, and similarly with longitudinal motion of bars, we're only going to consider small displacements from equilibrium. This gets real nasty when you go to what we call finite amplitude, not infinitesimal amplitude. So I've zoomed in on this scale. When I do a sketch like this, you know, this distance is much greater than that distance. They don't have the same scale. How else can I say this? They don't have the same, the y scale is not as much, we're zoomed in on the y scale, right? Okay. So immediately here you see what's peculiar about these waves is up here the material has been stretched compared to, in equilibrium it's going to be, you know, uncompressed or unextended, right? In equilibrium right here. Here it's stretched. What's happened here? When I go like this, what happens here? What happens down here? It's compressed. So at the same x location here, we have stretching, we have extension here and compression here. Somewhere in between there's going to be what's called the neutral plane. This is where it's neither stretched nor compressed. It's at its equilibrium, you know, value. You can show, and this is, I think this is very plausible, that for small deviations from equilibrium here, the neutral plane is halfway between. But if you go to finite amplitudes here, if you go to big amplitudes, this is going to get all much more complicated, I'm sure. I've actually never seen any work on that, but you know it's out there. Because, you know, this is real engineering type stuff, right? So there's going to be results on this, like I-beams. So we call this the neutral plane here. It's neither stretched nor compressed. It lies at the center for small displacements. We will use y here to be the displacement of the neutral plane from equilibrium. So that's going to be that's the variable we want. We want to find. Our goal is to find the wave equation for this system for the variable y. And you might wonder, why am I emphasizing that? Well, because we have to introduce a ton of other quantities in order to get to this. No one's found an easy way to do this, like with strings or longitudinal motion on bars. But that's what we're after. We're after the wave equation, the equation that describes y. And y is, of course, a function of x and time. Okay, so let's look at a differential little tiny element of the bar here. And in general, it's going to have some, it's going to be bent. It'll have some bending like this. Oh, I just noticed something I never noticed before. We chose this to be symmetrical, but it doesn't matter. You know, it could be, it doesn't have to be symmetrically bent about here. There's nothing wrong with doing, you know, this. Okay, and again, we're exaggerating the motion. This is all ultimately going to be just slight deviations from equilibrium, so that we end up with linear equations. All right, so let's look at some quantities here. This dx here is the unstretched, stretched or uncompressed. This is the neutral plane. Okay, so this length here refers to the bar, the material. It's neither stretched nor compressed because this is the neutral plane. They're stretching up here and compressing down here. This will the ends here will cause subtend some angle here. This really should be called d theta. To do this, it's not going to matter. This is just inserted momentarily. We're going to eventually want to get rid of it. We want to head towards y. But to be consistent, we really should have. I probably got this from KFCS, but I can't remember. We really should put a d theta here, but it's not going to matter. Now, because we have a lot going on in this direction, we have stretching up here and compressing down here, we naturally need to focus on an element. Okay, we've got an element going this way. We've got an element dx of the wire, but we have to, of the bar, but transverse to it, we have to specialize to a differential area here. Because you go at different points along here. So this is compressing down here, it's stretching here. So we need to make this a differential, much smaller than this differential, if you will, okay? So this is, I'll call this a filament. Here it has some area ds. And now, by doing this, things are changing negligibly across here. Okay, this is just stretch. This is like a bar. This is like the bar that we were considering before, you know, longitudinal waves on a bar. Now up here, this is going to be stretched a certain amount. We'll call that delta x. Okay, compared to equilibrium, this will have stretched. Down here, it will have compressed. All right, and this filament is some distance r from the neutral plane. Incidentally, just about all of these quantities are signed quantities. They can be positive or negative. And for example, this r right here, negative r will, we want to have this as a signed variable because we want to be able to, this is going to be r is equal to 0, and we want to be able to have a unified mathematical description for going this way and going that way. So there's going to be a sign difference between those two directions. And similarly with these forces here. Okay, so this is right, at this moment, this filament here is stretched. So it's going to be, what kind of force is it going to be exerting on this little cross-sectional area here? A force this way, right? Because it's stretched. It's stretched, so it wants to go back, so it's going to be exerting a force like this. I've drawn the force this way because this is the positive direction. But at this moment, in this situation, The force exerted on the end here by this filament will be running this way. And remember this convention that we used for longitudinal motion? By convention, this force here is the force of the left part of the bar on the right part of the bar at a point here. Remember that? We have to keep the signs straight here. Okay, oh, and the neutral plane will have there'll be some radius of curvature here. Okay, we'll call capital R. This is for the neutral plane. Okay, so that's setting things up, but before we dive even more into this, I want to point something out here that's interesting. What's responsible for the stiffness here? You know, to have waves, you got to have inertia and stiffness. You got to have something wanting to return the system to equilibrium, to have oscillations or waves. What's responsible here for that stiffness? Weird. Well, that's not a well-stated question. What quantity plays an important role here in making this thing want to go back like that? Well, it comes down to this filament here, and when you stretch a filament or you compress it, what dictates dictates the stiffness? I still haven't heard it. Young's modulus. That's what I was looking for. I would have given it away if I said what parameter. I should have said what parameter. It was not a well-posed question. I admit it. But what you want to see here is that Young's modulus is going to be involved here. It's at the heart of the stiffness here. You know, that distinguishes one material from the next is going to be the Young's modulus. You can see it here. Because the greater the Young's modulus in here, the greater the force is going to be here. Okay, so that's at the heart of all this, is the Young's modulus. All right, so let me remind you, this, we derive this because we've taken this to be small here compared to the bending here. We can just use our one-dimensional result for the force, longitudinal force of a bar. We derive that, and we refresh your memory. Here it is. Here's the Young's modulus playing the role of the stiffness. It's proportional to the Young's modulus, and it's proportional to the cross-sectional area, as it must be. And then here's the strain, the rate of change of displacement with respect to x. That's the strain. So this, we're just lifting this from the previous part, what we did on longitudinal motion. Now, what is this? This is the strain here is the rate of change of displacement with respect to x. Well, we're zoomed way in here. This is a differential element. So we can get the strain by simply taking the change in distance, delta x, divided by the original, the equilibrium distance, which is dx here. So the amount that this is strained is its change in length compared to what its length is in equilibrium. Oh, I just saw some problem here. Okay, I know it's bothering you. I can feel it. So this thing is stretched, right? And it's going to have some equilibrium length. Is that equilibrium length equal to this length? Not really. But remember, this is all going to be tiny. This is all going to be small here. So that's why I didn't notice this before. Let me make a note of this so I can think about it later. The equilibrium length dx is not. No, I take it back. It's not going to be. Look. So this is right along here. It's neither stretched nor compressed. Okay. I have to think about this. Yeah, I think there may be a little bit of a problem here. When we look at this filament, it's going to have an unstretched length. And it's not obvious that it's equal to dx, is it? But it's going to be, I think it's probably going to be one of those higher where it's approximately true. Because remember, we're taking small displacements from equilibrium. But it does look like there's an assumption here. So I'm going to make a note of this and think about it.
So what's the problem that you're trying to figure out?
Here's the problem. If you look, we're going to set the strain here. the rate of change of displacement with respect to x, we're going to set it equal to the change in length of our filament divided by dx. What should be there is, whoops, wrong way. What should be there is the equilibrium length of this. You know,
Is that not the same?
it is going to be the same.
It's just a
Yeah, I think it's the same, but I still want to think about this, okay?
It's the same when R is very big. R is very big.
You know, in equilibrium, this thing just comes down like this. So dx is going to be, yeah, I think it's got to be true. I think what I'm worried about is higher order, since a nonlinear effect. I'm sorry, Evangelist, say it again.
When R is very big, it's equal.
Yes. That's all part of our linear small displacements here. When we say small displacement from equilibrium, we're also going to make, remember in the string with small slopes too? It's the same way here. And it's also small second derivative too. We have to go actually one more derivative here. All these things are assumed to be small. So I think what I'm worried about here is higher order, okay? All right. So we've got this, all right? Now, this is not good. Remember, we're after y, and we're in the wrong direction here, delta x, right? So how can we do this? Well, this takes a while. The next thing to notice here is that this angle theta, we can write down theta two ways. This angle theta, which really should be d theta, we can write it as dx divided by r, which is going to be the same as this, which is dx plus delta x, divided by this r, which is a little bit greater. So once you see that written down, I think you'll buy it. So we can write the angle theta as the arc length r, as the arc length dx. This is this distance right here. By definition of radians, you know, this angle here is this divided by that. But we can also write it referred to the filament. And that gives us this right here. Now you can forget about theta. I think we're probably done with theta. I'm not sure, but I think we're done with it. This is going to tell us, with very simple algebra here, tells us what delta x over dx is. And it's all right here. It's very simple. You can do it in your head. We can replace delta x over dx with little r over big R. And when we do that, this is what we find for the force. Okay, so that's this force due to a filament here. And remember, we're just doing small linear deviations, small deviations from equilibrium. At this moment, the actual force here, remember this is just the positive direction. The actual force here is pointing this way. On the other side here, where is that force pointing? This way, right? And again, remember, these are small. These are approximately horizontal. Those forces are going to cancel. So there's no net longitudinal force on the bar, okay? But that's not to say there's no transverse force. There's got to be a transverse force, as we'll describe later. But even though there's no force, and this is not obvious here, why this would be important, even though there's no force, there is a torque. If you look, for example, about this point, about this axis right here, or this point, for this situation right here, there's a force there, force this direction. Down here, it's this way. There is a torque. So a torque will tend, right at this moment, the torque is tending to rotate this way. There's a torque, there's a counterclockwise torque. And it turns out we need to calculate that. You might say, well, don't we just want to describe the motion, just come up with the restoring force here and find an equation for y? Yeah, but we have to go through all this other stuff to get all this information in here. So we need to deal with that torque. Engineers call it a bending moment. Torque is force times distance. Force times distance. So our little filament here is exerting a force dF given by that. It's some distance from the neutral plane. So it contributes this amount to the torque. So the word moment here signifies distance, force at a distance. So bending torque, a bending moment is the same as a torque. So here's the torque, and we use M probably for a moment, but I don't know. We need to do this integral here. So we take the force here from the filament, put it into here, and then we integrate over all filaments. The Young's modulus is a constant. This distance r is a constant. You can see that. This distance r is a constant. Because we're doing this all at one moment, right? At one time. What we're left with here is a purely geometrical quantity. It's the integral. This has nothing to do with directly with the how to say this. It's just a geometrical quantity. Okay, there's no Young's modulus in here. It's what you need to do is, given your cross-sectional area, whatever it may be, if the circle is like this, and here's your neutral plane, you've got to integrate over all that whole surface there, the square of the distance from the neutral plane here. And this is sufficiently important that it's got a name. It's called the radius of, it's connected with the radius of gyration. We use kappa for the radius of gyration, and the definition is that the square of the radius is this. So it's the integral of r squared over the area normalized to the area. So this, you know that this is going to have dimensions of length squared, right? Because of we've divided out the s's here. So that's why we have to have kappa squared there. So when we do that, this is, I mean, as we noticed before, what's happening here on a bar is going to depend upon its cross-section. Depend upon what we now know as the radius of gyration. This thing behaves, the I-beam obeys completely differently when you look at flexure this way, when you look at flexure that way. We actually have some of this in the demo lab. There's a demo that we do with it. It's a plastic I-beam. It's not the big heavy stuff, in bridges and stuff like that. But it's just little stuff, and it's great to play with it. You can make a pendulum out of it, put a mass and clamp it, and you can get, in this direction, oscillations of a certain frequency, and you can pull it this way and guess what the difference is with those oscillations. These are much faster than this, dramatically faster. It's actually used in a demonstration of a Foucault pendulum, but I shouldn't have said that. Don't worry about it. All right, so where were we? The radius of gyration. Now, before we go on, we better talk about different radius of gyrations. This is just a simple integral calculus, purely geometrical thing. You can show, and we might show one of these in a problem set. I have a vague memory of that. You can show that for a circular cross-section, the radius of gyration is the radius of the circle. That's what this A is here. Yeah, there, divided by 2. For the rectangle, transverse to B. Now, for a rectangle, you've got to, where's the neutral plane, right? There's two possibilities. It's here or it's here, and you're going to get different answers. In fact, you can see that if we take, let's say we take the neutral plane to be here, A is going to scale out. Because remember, it's the integral over the surface area divided by the total surface area. So if this is our neutral plane here, as opposed to here, then A is going to scale out, and it's just going to depend upon B, and it turns out that it's B over the square root of 12. Okay, so back to our calculation here. You'll notice we have this R floating around, and we got to get rid of it. And what this is, incidentally, is if I've got a bar doing something here, at any, it's much more general than this. If you have a curve in three-dimensional space, has anyone ever had any differential geometry? I don't know if people anybody have any? Okay. So here's a curve in 3 space, and it can be doing anything in 3 space, right? Three-dimensional space. And you pick any point, it's a smooth curve. It's got to be smooth curve. You pick any point here. There's going to be a radius of curvature at that point. You're going to, and the way to think about it, and it's quite simple, is there's going to be a circle here. of some radius, we'll call it r, it will have some origin, and that origin can be, this can be complicated, right? This curve is doing things in 3 space. So it turns out differential geometry tells you how to find the center of this circle and the value of that r, and that's called the radius of curvature of the curve here, how it's curving. So you can always fit that. I think that's very plausible, right? Okay, now it's not difficult to show, and I remember doing this a long time ago. Let's get back to our 2-dimensional case here, okay, rather than 3-dimensional. I just wanted to point out that it's very general. Let's get back to this case right here. It's not difficult to show that for small deviations from equilibrium here, that this radius of curvature is identical to the second derivative of y with respect to x. All right? Now, when I have, this is where we're headed here. I've got a curve here, it's doing something like this. The first derivative of y with respect to x is just the slope. The second derivative is how that slope is changing, right? So clearly, if the partial of y, I'm going to use partials because there's time here. If we have a situation where this is true, what's the curvature here? No, this is just something that's like right here, locally straight. There's no curvature. The radius of curvature is infinite. Would be infinite. But when this is not equal to 0, we're going to have, getting away from this point, like here, for example, right here, the second derivative is going to be negative here, right? Because the first derivative is decreasing. So we're going to, at this point, we're going to get, just for definiteness, and there's clearly some curvature there. And you can show that, excuse me, that's better. You can show here that the second derivative is identical to, it is the radius of curvature. And that's reasonable, but it's not exact, okay? There's a nonlinear relationship. It's a little bit more complicated. It's more complicated than that. But for us, for small deviations from equilibrium, we use this approximation. Has anyone seen this before? Does this ring a bell? Yeah. Okay. Okay, so where are we? So this is how, finally, and we're not done yet, but this is how we can finally get y into the calculation here. We replace 1 over r with the second derivative, which is, this is reasonable, that there's this relationship here. When this gets small, we know that means r is going to have to get big, right? When this goes to 0, r goes to infinity. We know that physically has to be the case, so this is reasonable. Okay, when we do that, we can now write down, we can get rid of, in our moment equation here, we can get rid of the radius of curvature here in terms of the second derivative with respect to y, and we get this. So this is an important equation on the step to deriving the wave equation. And sometimes, I want to warn you about something here. Sometimes we need to use these equations for like boundary conditions. We did, if you think back, we did the same thing with a string. Okay, we just can't, we have to supplement the wave equation. Almost always we have some kind of boundary conditions. So to mathematically describe those boundary conditions, we need to rely on these other relationships. We did this with a string. Okay. Again, these are all signed quantities, and remember we decided, well, it's best just to go to the next page here, I think. I don't like this. I want to say this differently. We have this, we know we have a bending moment. Here it is. We've got a formula for it. This describes at every point along the bar, at any point in time, what this torque, what the torque is. This torque can give rise to a force, to a restoring force. I don't know if that's the right way to say this. I think it is. And let me explain here. we know that there has to be forces here. If I take this and hang a weight on it and it goes down like that, I know that the bar is trying to force an element here to go back to equilibrium, right? So we know that there has to be forces here. And this is kind of a trick, how we get those. We can get the forces from the bending moment. So let me describe to you how that works. First of all, we take an element, this is from x to dx, and we look at all the forces and torques on that element. So at x here, there's going to be, in general, a torque. Now, I'm not saying that the torque is necessarily in this direction. I'm just saying that's the positive direction for a torque. Okay, and it'll have some value. We have to allow for some transverse force. We know that there has to be transverse forces here. So we're going to call this F sub y transverse at this location x, and that's the positive direction. Now, these represent the force and torque due to the left side of the bar. Over here, we need the force and the torque due to the right side of the bar. So we're going to take, first thing we're going to do is this torque right here. It's going to be evaluated at a slightly different point, of course, because we've displaced over here. And we have to put a minus sign here. And the reason is, what we care about is the force of the right on the left. This is the force of the left on the right. So we have to put a minus sign. And we've been through this before, actually. I'm just emphasizing it now. We have to do the same thing with the force. This part of the bar will be exerting, in general, some kind of force, transverse force here. Over here, it will be at a different x, and we have to put a minus sign because it's the force of the right-hand side. Okay, so now for the trick. And some of you may have heard this before. If you're any mechanical, we decided there are no mechanical engineers in here. Is that right? That's surprising. Usually there's a couple. The trick is this. We have torques here. We have a torque here, and depending upon our origin, these things can exert torques. What's the total torque have to be on a little element of a bar? You can probably guess. We're going to shrink this down to 0. The torque has to be 0. You can show this. And I made a comment. If you're interested, you can look at this comment right here. If the torque were not 0, we would have infinite angular acceleration. Because the moment of inertia is going down quickly, right? It depends upon the square of the length here, the moment of inertia. Remember Newton's second law for rotational motion? The torque is the moment of inertia times the angular acceleration. So it's going down quickly here. I made a specific comment there. So if the torque doesn't vanish and the limit as this shrinks goes to 0, you're going to get infinite angular acceleration. So that's the trick here. That's how we determine what these transverse forces have to be. It's kind of an unusual thing. You know, usually when we need to know a force or something, we just calculate it. This is done sort of indirectly here. It's all tied together though. This so-called shear force, this transverse force here, is connected with the bending moment. Okay, so here is the fact that the torque must vanish. Oh, for torque we have to pick an origin, right? Torque is force about a point. So let's pick, it doesn't matter where you do it, you're going to get the same answer. Let's pick our origin to be here. What is the torque exerted by this force? Anybody?
0.
0, because the moment arm is 0. Torque is force, you know. If I got an origin here and I got a force here, the torque is this force times this moment arm distance. But if the force is here, the moment arm distance is 0. So this doesn't contribute to the torque about this point. This, we got to do this, okay? And this, these torques just add. It doesn't matter that there's a distance of separation here. So the total torque is this plus this, and now we get a torque from here. That's going to be how we determine this. It's going to be this force times this distance. So that's what I've written here. Here's the total torque about a point here. And this has to be 0, or we would have, in the limit as dx goes to 0, or we would have infinite acceleration. So we do our usual Taylor expansion here. We can expand this in a Taylor expansion. The value of this, because dx is small, is going to be the value at x plus the derivative of m with respect to x times dx. So because of the minus sign, I get this. We do the same Taylor thing here. We did this before for the string. We get this. And now you got to notice, this threw me when I was looking at this last night. You'll see that we're multiplying this by dx. What's dx squared? 0. Okay, as we take the limit as dx goes to 0, and that's what we mean by writing dx actually. It's higher order. So this term is not there in the limit as dx goes to 0 because it's going to 0 very quickly here because it's squared. And we find a formula for the force. It's the rate of change. It's proportional to the rate of change of the bending moment. If the bending moment is uniform, there's no force. So now we can substitute in our previous expression for the bending moment, and we get this. And here I think I explicitly, we're going to definitely need this for boundary conditions. That's why I put a box around it. But what we want to do next is now finally we can derive the wave equation. After all of this work, we now have enough, we've built up enough mathematical relationships that we can derive the wave equation. So here we go, Newton's second law, right? When we look at our bar here, we care about this transverse motion. The net force is this force plus that force, and it's going to be the mass times the acceleration. So here are the two forces. Again, we do the standard Taylor thing. As dx goes to 0, we just need to worry about the first order Taylor correction of this. So we get this, just like I was saying before. This is the force. It must be the mass. The mass is the density times the volume. This is the volume. And times the acceleration, which is 2 time derivatives on y. And now the dx's cancel. And we substitute in what the force is. Here's our expression for the force. You'll notice the derivatives have built up here, starting with the curvature being the second derivative. Now we had to take another derivative. This is the third derivative. Now we take even another derivative. Because what's important here is how the force is how it's changing. If it's not changing, we don't have a net force. So this quantity will be proportional to the fourth derivative of y with respect to x. So this is what we get. We clean it up a little bit, put it into a sort of a standard form, and we get this equation. And that is not the wave equation, is it? First of all, it's got 4 derivatives, not 2. And second of all, there's not a minus sign, it's a plus sign. So this is not the wave equation. So what you would immediately expect here is we're not going to get this simple wave equation property of different wavelengths all traveling at the same speed. You should immediately suspect, I mean, it's guaranteed. It's essentially, I think it's guaranteed. And we quantify that in a real simple way here. We assume a wave of a single frequency, a definite frequency. Okay, this is a nice sinusoid here. It has a definite frequency and a definite wave number, or wavelength, right? K is 2 pi over the wavelength. We assume a solution like that and see what it takes to make it work. So we take this, substitute it into here, and you can see the 4 x derivatives are going to bring down a minus ik to the 4th power, right, by the chain rule. So what happens when you do that? What's minus I to the 4th power? It's just 1, right? So that's why we have a 1 here. I've got to take 2 time derivatives. That's going to bring down a minus omega quantity squared. It's going to bring down an I omega quantity squared. So we do get a minus here. That's good. And now we can solve for the dispersion. Dispersion relationships are usually stated as omega is a function of k. They're usually written like this. And there are all kinds, I've warned you guys, there's all kinds of wave systems out there, and they don't all satisfy the wave equation. And so the first thing you do when you get something that doesn't satisfy you don't get the standard wave equation, where omega is equal to ck, right? ck, where this is a constant. These are dispersionless or non-dispersive. Either word is fine. Non-dispersive waves. They're called that because all the All the components, every wave in here, no matter what the wavelength or the frequency, they all move at the same speed c. We don't have that here. And the information is in the dispersion relationship, which is just gotten right from here. So one of the things we can get from this is, what is the velocity of a wave of definite frequency? Well, we call it the phase velocity, and remember it's omega over k. This is just distance over time. Right? This is 2 pi over the wavelength. This is 2 pi over the period. So this phase velocity here, for a nice wave of definite frequency, is just distance over time. You can't argue against this. Okay? This has got to be the velocity of a wave of definite frequency. We can take this omega, this expression, substitute it in, and we get this. Equivalently, we can express it instead of expressing it in terms of k, we can do it in terms of omega. Same mathematics, they're equivalent. And you get this. You can look at it either way. Whatever one people use is just for convenience. The point is, the speed of the wave depends upon the wavelength or the frequency, or equivalently the frequency. We have dispersive waves, right? Yeah, here. So these are called, yeah, I don't know if I actually said it here. These are dispersive waves. So what waves travel faster? The higher frequency, which means the smaller wavelengths. Smaller wavelengths, higher frequency waves travel faster. It's the opposite of gravity waves on the ocean, deep waterways that we've talked about before. There, for deep waterways, it turns out, this is a constant, right? It turns out this is to the first power and the square is over here. So omega squared is equal to gk. I don't think I mentioned this to you before, but that's the mathematical dispersion relationship for deep water waves, where the depth is large compared to the wavelength. And there it's the, remember the ancient mariner thing? It's the long wavelengths that travel faster. We could start this, but I'm exhausted. This derivation is exhausting. Right? It's not easy. So I think we should just stop here. So does anybody have any questions or comments? We have a minute or two, so if something's bothering you, go ahead and ask. Okay? And I'll tell you, and I've told you this before, and I want to tell you again because it's important. One of the reasons we do this, and all professors agree on this who teach this stuff, or at least the ones that the 2 or 3 that I've talked to, believe that a big importance behind this is so that you get exposed to waves that aren't dispersionless. Okay? Get away from this usual thing. And it's just important to have that knowledge. And it's important even if you're just going to be restricted to acoustics, because acoustics is not always non-dispersive. When we introduce dissipation or something, we're gonna not get the wave equation anymore. So you need to know how to deal with equations that aren't necessarily the standard wave equation. So there's 2 kind of different reasons. That's why we do it. It's complicated. You can see from the we spent almost, like as I mentioned, almost the whole time just deriving this. But you know, I think it's worth it. Maybe you don't, but I think it's worth it. Especially because it broadens us, right? Gets us thinking about different things. And there are a lot of wave systems out there that, like I said, are not dispersionless. Okay, any questions or comments? Okay.